Code reviews. Developers don't like code reviews because it causes them work. Usually find things during a code review that have to be fixed. However, security people love code reviews because it prevents work down the road. You're saving all of these vulnerability exploits and attacks against your applications by doing code reviews. So a code review is the notion that you're going to go and look at your application source code to try to proactively identify potential vulnerabilities. You're trying to find spots where an attacker could do SQL injection, could do buffer overflows. You're looking at the application to figure out what could go wrong at the code level. This is a crucial part of the software development lifecycle, or SDLC, as it's a preventative measure. It's to help eliminate the opportunities that attackers have to take advantage of your application or exploit them in the wild. There are a lot of different testing techniques out there, a lot of different code review techniques. The first we'll talk about is black box versus white box testing. Black box testing is the idea that you have no prior knowledge of the system, but you're going to try to test against it or attack it. White box testing is a slightly different version of that, where you do have knowledge of the application. Perhaps you have the code sitting in front of you, you've got a network diagram, but you've got some knowledge of the system that you are testing, and it allows you to do perhaps a more targeted focused test as opposed to a broad-based approach that you would do with black box testing. There is dynamic and static testing from a code review perspective. Dynamic testing is you're looking at the system and observing it in real time while executing the program, so you're kind of stepping through things. Dynamic testing is done through sandboxing, usually virtual sandboxing, where you've got a copy of the program running, you're doing memory analysis on it, you're looking at the code through a debugger. That's dynamic testing. Static testing is where you're looking at the system or the code while it's not being executed. So you've got just a copy of the source code in front of you and you're looking through it. That's static testing. There's also manual versus automated testing. Manual testing is the idea that you've got somebody who's manually going through the source code, typically with a pen and paper or maybe keyboard and screen, and going through the code and looking at it line by line to see what could be wrong with it. There are automated tests as well that you can run, specialized programs to do code reviews or fuzzers that will actually go through and do automated testing. And the good code reviews, the very in-depth code reviews, usually use some combination of all of these. Good code reviews will almost always do automated testing and then supplement it with manual testing of critical functions because the automated testing can't catch everything. And there's no computer power out there like what's in between your ears. So the manual testing, if you find good code reviewers, can go a long way to supplementing what you do with the automated side. Fuzzing. We talked about this a little bit, but fuzzing is this idea that you're using automated methods to find input validation errors. With fuzzing, what you're essentially doing is throwing all sorts of combinations of input to an application and seeing where it craps out on you. It's a really popular tool for finding operating system bugs, application bugs. But if you look at the diagram here in the center, this really exemplifies what's going on with fuzzing. Here on the left, you're starting the actual program. You start the fuzzing process by providing some type of test input or strings or URLs or something to the application. And then you're looking at the program. Is it still running? Did it crash? If it's okay and the program's still running, that means our input was benign. We'll come up with another set of input and try it again. And what we're looking for is the combinations of input strings or actions that cause the program to either crash or hang, because those are the interesting cases. Those are input did not provide expected outcome, right? So when you check the program health, if you see that it hangs, essentially kill the program, start it again, and start your test again. But note the fact that the crash, or that the input that you provided caused the program to hang, because now you can provide that to the developer and they can go fix that because it was an unexpected case. If the program actually crashes, this is an interesting one because that means that the application has crashed, and maybe there's an opportunity to write some type of buffer overflow or heap overflow or something like that. There's some opportunity to write an exploit for this that might be able to take advantage of your program, whatever it is that you're fuzzing. So you want to triage that crash and see if you can understand what that crash is actually caused by, what are the parameters around that such that maybe it could or could not be exploited. But you want to save that test as well and store that with your test results, because that's definitely an input case that you want to look at and have the developers fix as well. This is why I said that this is a nightmare for developers. They don't like this because it causes them work every time you find one of these hangs or crashes. But from a security perspective, I like this because if I can find this now, a year from now when my program's out there in the wild, I'm not going to be responding to security incidents as a result of this bug. So a good example of this, you can find these tools on the Kali Linux distribution from Offensive Security. This is a program called Spike. And here in the screenshot in the, on the left side here, we're actually fuzzing a FTP server with a set of known inputs. And so what we're doing is providing, on the user input string, instead of providing a username, we're providing all sorts of combinations of data just to see if the FTP service will choke on it. And so it's going to try different character combinations, different letter combinations, and at some point you may or may not find that the program crashes. In this particular example, the program does crash, and it was with an input of a bunch of capital A's, or hex character 41. How would you find that if you were doing this manually? Simply by luck. You just happened to stumble on it. Or if you were actually reviewing the source code, you might actually see that there's an unbounded string check or something like that in the code that you could think about and go, oh yeah, well maybe that will cause a crash down the line. But by providing an automated fuzzer like Spike, you can craft all of those inputs and even have the program generate inputs for you, random inputs for you, and just throw it at the program, let it run overnight, and see what it does. Testing considerations. Before you run off and fire a code review or fuzzing application at your services that you want to test, take a look at the attack surface. Understand where user input occurs, what type of application you're actually running. Look at the results that your testing tools will provide to you. Are the tools usable? I mean, do they make sense in your organization from a testing perspective? Do the tools support the technology that the application was built on? You can't use, say, a Python tester on a assembly level program. It just won't work. So make sure that you're using technologies that are compatible with each other and you're selecting tools that work. And also look at the performance and resource utilization. If these tests require massive amounts of computational power because it's trying so many combinations, or you need to parallelize things because you've got so many potential test cases, make sure you consider the, the fact that you might need some additional resources to run this test. All of these considerations should go together when you're starting to think about, well, what tool am I going to use for this? Am I going to use Immunity Debugger to do things manually? Am I going to use Spike to do automated fuzzing? Am I going to go grab 10 guys, put them in a room, and throw pizza at them for 2 weeks while they do a code review? All of these types of considerations should go into figuring out whether you are using the right tools or not. From a system-level testing perspective, you want to make sure that the testing that you're doing is accounting for all the possible cases that you can think of. Now, you think of all the potential inputs that your program might see. It's huge. It's a huge space. But look at the things that are most important to you and use that to kind of refine what tests you actually run. So you might be looking specifically at things like privacy-related issues. Can I compromise data out of this thing? Performance issues or stress conditions, usability concerns, compatibility with other applications or interface testing. All of those sorts of things you might want to use to be able to refine your test and come up with a smaller test space. Otherwise, it's a pretty big unbounded problem. And then maintenance considerations. So once you've run your test, that's great, but there are things that you need to do to follow up on that. Every time you revise your application, it's probably a good idea to revise your testing plan and make sure that how you're testing your application still is in line with how the application works. And that takes close coordination with the developers and testers to make sure that they have the right test plan built. Anomaly evaluation, let's say you start seeing the crashes, you're seeing the hangs while you're doing automated fuzzing. Dig into the code and figure out what is causing that. I'm willing to bet that you're going to find one of your coders is using unsafe string functions, or there's some coding practice being used that's causing these particular bugs. And in that case, if you understand the root cause of that, you can fix that. Send the guy to a secure coding class, or specifically look for that type of error, and that will give you a much easier way to reduce your attack surface by eliminating those errors at the source. Once you find problems, making sure that you identify them, track them, and actually manage the changes associated with that in some guided fashion, such that the testers reported an error over here. You don't want that to get dropped and not make it into the actual build release. So as you're going through your testing, make sure you're using, pick anything. GitHub, could be an Excel spreadsheet, whatever issue tracker, bug track that you're using. Make sure you put all of that information in such that you can track it all the way through to completion. And when you're iterating on the actual task to fix this stuff, you can keep track of it, and you know what's been fixed and what hasn't been fixed. And then, of course, update the documentation. You might find that certain user inputs are coming from users because they don't know how to use the system. So as part of your testing, make sure you update your documentation. And all of these considerations go into effect after you've done your test and you need to improve your application as a result of that.